In this episode, we are looking at a part of computer support that sounds exciting on the surface, but causes a surprising number of avoidable problems when people rush into it. And that is the world of expansion cards, cooling choices, and hardware upgrades. New learners often assume that upgrading a system is mostly about buying a better part, installing it, and enjoying instant improvement. But technicians learn very quickly that almost every upgrade changes something else inside the machine. A new card can demand more power, create more heat, block airflow, take up physical space, or expose a weakness in the system that was not obvious before the upgrade happened. Once you understand what expansion cards do, how cooling methods affect reliability, and how technicians judge what a system can realistically support, you start to see that good upgrade work is less about chasing the biggest possible part and more about building a balanced, stable, and supportable system that continues to work well after the excitement of the upgrade is over. Before we continue, a quick note. This audio course is part of our companion study series. The first book is a detailed study guide that explains the exam and helps you prepare for it with confidence. The second is a Kindle-only ebook with 1,000 flashcards you can use on your mobile device or Kindle for quick review. You can find both at Cyber.Me in the Bare Metal Study Guide series. An expansion card is a hardware component that adds a function the system either does not already have or cannot perform well enough with its built-in features. These cards connect through a slot on the motherboard, most commonly a slot based on Peripheral Component Interconnect Express, PCIe, and that slot is not just a physical opening but part of the system's communication path, power design, and layout planning. A technician thinks about expansion cards as add-on capabilities, which means the question is never only whether a card can be installed, but whether it belongs in that particular machine and supports the user's real needs. That matters because many systems already include audio, networking, basic graphics, and storage support on the board, so adding more hardware only makes sense when there is a clear reason, such as better performance, additional ports, specialized functions, or replacing a failed built-in capability with something the motherboard no longer provides on its own. The most familiar type of expansion card for many people is the graphics card, because visual performance is one of the easiest upgrades for users to notice. A stronger graphics card may improve gaming, creative work, visual acceleration, or support for multiple displays, but technicians do not choose one just because it is faster than the old part. They look at the size of the card, the cooling design around it, the amount of power it needs, and whether the rest of the system is strong enough to benefit from it. Because a powerful graphics card installed into a weak or cramped system can create a long list of problems without delivering the improvement the user expects. Other common expansion cards include network cards for wired or wireless connectivity, storage controller cards for additional drive support, sound cards for specific audio needs, and specialty cards that help with capture, communication, or business functions. And the technician's job is to judge whether each one solves a real problem instead of simply making the inside of the computer more crowded and complicated. That decision starts with a basic truth that beginners sometimes overlook, which is that not every system can support every expansion card even when the card and slot seem roughly compatible at first glance. A motherboard may have a free PCIe slot, but that alone does not prove there is enough room in the case, enough electrical support on the board, enough cooling nearby, or enough clearance around other components to make the installation practical. Some cards are long, thick, and heavy, while others block neighboring slots or sit close to drive cages, cables, or front fans in a way that makes service harder and airflow worse. Technicians also pay attention to whether the case uses full height or smaller brackets, whether there are enough rear openings available, and whether the card will fit without putting physical stress on the board, because a free slot is just one piece of the compatibility puzzle and is rarely the only thing that determines whether the upgrade is a smart idea. Power is often the hidden reason an upgrade fails, especially when a system seems to work briefly and then becomes unstable under real use. A graphics card, storage controller, or high-performance networking card can increase demand on the power supply unit, PSU. And that demand does not stay isolated to the new card because it affects how much stable power remains available for the rest of the system. Technicians look at total system needs, connector availability, and the quality of the existing PSU before recommending an upgrade, because a weak or aging power supply can turn an otherwise valid improvement into sudden shutdowns, restarts, strange startup behavior, or hardware that only fails when the machine is working hard. This is one reason experienced support people do not trust a system simply because it turns on after the upgrade, since a machine that powers up on the desktop may still collapse during gaming, design work, large file transfers, or any other task that pushes the upgraded hardware into the range where real power weakness becomes visible. Heat is the other major cost of upgrades, and many users underestimate it because heat does not sound as dramatic as a missing part or a failed boot. Every active component produces heat, but stronger parts usually produce more of it, and when that extra heat stays trapped inside the system, it can shorten lifespan, reduce performance, and create failures that seem random until someone notices the thermal pattern behind them. A technician thinks about cooling as part of system stability, not as a cosmetic extra, because a hot computer may slow itself down to protect its hardware, may become noisy as fans work harder, or may shut off unexpectedly when temperatures rise past what the system can handle. This means an upgrade is never judged only by performance numbers, since the real question is whether the machine can remove the added heat well enough to keep that performance steady over time instead of delivering a short burst of improvement followed by throttling, crashing, or premature wear. Cooling methods can be understood more clearly when you stop thinking of them as special enthusiast gear and start seeing them as simple ways of moving heat away from sensitive parts. Some components rely on passive cooling, which means a heat sink spreads and releases heat without a dedicated fan, while many systems use active air cooling, where fans push heat away from the processor, graphics hardware, and the inside of the case. More advanced systems may use liquid-based cooling approaches, but the beginner lesson is not that one method is always better than another, because the right answer depends on the system design, the amount of heat being created, the user's noise tolerance, and the need for long-term reliability. Technicians often prefer solutions that are easy to maintain, appropriate for the workload, and match to the physical system, because a complicated cooling setup in the wrong case or in the hands of a user who cannot maintain it may create more support problems than a simpler and more practical air-cooled design. Case airflow is where many upgrade decisions either become wise or become messy, because airflow determines whether the heat from upgraded hardware has a clean path out of the machine. A system can have strong individual coolers on important parts and still run too hot if cables block airflow, if intake and exhaust balance is poor, or if a large new card traps warm air in the center of the case. Technicians look at the case as an airflow environment, which means they care about fan placement, dust buildup, component spacing, and whether hot parts are sitting too close together to cool efficiently. This is why simply adding more fans does not always fix a hot system, since poorly planned fans can create noise and turbulence without improving the real movement of air, and a well-planned layout with fewer properly placed fans often keeps a system steadier than a louder machine that seems powerful but moves heat in an unfocused and ineffective way. When technicians talk about hardware upgrades wisely, they are really talking about system balance. Upgrading one part should make sense alongside the processor, the memory, the storage, the power supply, the motherboard, and the cooling design, because a system is only as stable as the weakest support around the upgraded component. A strong graphics card paired with too little memory, a fast storage upgrade paired with an aging processor, or a better processor paired with poor cooling can all leave the user disappointed because the system remains limited or becomes unreliable in a new way. This is why support professionals ask what the user is trying to improve before recommending hardware, since the right upgrade for gaming, office productivity, content creation, remote work, or lab practice may be very different, and a balanced improvement often delivers a better real experience than an expensive single-part upgrade that leaves the rest of the machine struggling to keep up. Compatibility planning also means knowing when a system has reached a practical limit and should not be pushed much further. Some computers were designed with narrow thermal margins, limited power headroom, few expansion options, or very compact internal layouts, and those design choices may make them reliable for their intended job while also making them poor upgrade candidates. A technician does not take that as a challenge to force bigger parts into a small machine, because support work is not a contest to see what can be made to fit for one afternoon. Instead, they judge whether the board supports the new hardware, whether the case allows enough space, whether the cooling path remains acceptable, and whether the cost and complexity of multiple supporting upgrades are still reasonable. Because once a simple improvement turns into a new power supply, more cooling, additional cabling, and a cramped service experience, the upgrade may no longer be the smart answer it looked like at the start. Poor upgrade planning often reveals itself through instability rather than through a single dramatic failure, and that is why it can confuse beginners. The machine may boot normally but freeze during heavy work, restart without warning, run much louder than before, show visual glitches, lose network reliability, or become slower because heat forces parts to reduce performance and self-protection. A user may blame the newest part, but technicians know the deeper cause may be insufficient airflow, a weak power supply, a crowded case, an unsupported board, or a system that was never balanced for the new workload. These symptoms matter because they teach an important support lesson, which is that success is not measured by whether the upgrade can be physically installed, but by whether the system remains predictable, cool enough, stable enough, and easy enough to support after normal use begins, and the machine is placed back into the real environment where the user depends on it. A simple example shows how quickly good intentions can become a bad support outcome. Imagine a user with a basic desktop who wants better graphics performance, so a large graphics card is installed because it fits the slot and powers on during a quick test. A few days later, the system begins shutting down during heavy use. The case becomes much hotter than before. One nearby slot is no longer usable. Airflow from the front fans is partially blocked, and the aging PSU is operating near its limit every time the card is under load. Nothing about the original goal was unreasonable, but the upgrade planning stopped too early because the technician should have considered power demand, case space, thermal behavior, and the overall age and design of the machine before deciding that the slot alone proved readiness. That is the difference between installing a part and supporting a system, and it is why real technicians think past the first successful power on. A second example can be even more revealing because it involves smaller upgrades that appear harmless on their own. A system receives additional memory, a faster storage device, and an expansion card for more external connectivity over a short period of time, and each change seems sensible because none of them individually feels extreme. Yet the added parts increase heat, tighten internal cable space, reduce airflow around the storage area, and begin to expose that the system's original cooling and power design had very little extra capacity. Now the machine does not fail in a dramatic way, but it becomes noisier, less pleasant to service, and more likely to behave inconsistently during long work sessions, which means the user experiences the upgrade as a mixed result rather than a clean improvement. This teaches an important lesson for beginners, because support problems are not always caused by one oversized part, and can also grow slowly from several moderate upgrades that were never considered together as a combined change to the platform. There are also several upgrade myths that technicians learn to ignore. Newer is not automatically better for a given machine. Bigger coolers do not automatically mean better airflow, and a free slot does not automatically mean the system is ready for another card. In the same way, more fans do not always create a cooler case. Expensive parts do not guarantee noticeable improvement for the user's workload, and a system that survives a benchmark on one day is not automatically ready for months of dependable operation. The support mindset is calmer than the shopping mindset, because technicians care about fit, stability, serviceability, noise, temperature, and realistic user benefit rather than chasing the most impressive part name or the highest number on a product page. That steady mindset is what protects people from making hardware decisions that feel exciting in the moment but create expensive, time-consuming support issues after the machine returns to daily use. By the end of this topic, expansion cards, cooling methods, and upgrade decisions should feel less like separate hardware subjects and more like connected parts of one larger judgment call. A technician chooses add-on hardware based on need, checks whether the motherboard and case can support it, makes sure the power and cooling design remain healthy, and thinks about whether the rest of the machine can keep pace with the new part instead of becoming a bottleneck or a source of instability. Good upgrade work is not about proving that a component can be forced into the system, but about making sure the whole machine remains balanced, dependable, and worth supporting after the change is complete. When that approach becomes your habit, you stop seeing upgrades as isolated purchases and start seeing them the way experienced technicians do, as decisions that either improve the platform thoughtfully or slowly push it toward heat, noise, power trouble, wasted money, and avoidable support headaches.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.